I have all this time. Alright. We ready? Sweet. Okay. Hello everyone. Welcome. So we'll get started with our general if you're new. I don't think anyone here is new. Everyone looks familiar. That kid looks new.
Me?
No, Zach.
No way.
Just a reminder, we have CTF practice at 4 p.m. on Sundays in the lab. I know attendance to that has been pretty low, so if you guys are interested, go to that. We also have lab sessions on Monday at 6 in the lab. So yeah. Also, if you're not involved with the committees, join. Content, especially, if you need help. Chris, you put this in here. I think our power cables are nice and pretty now.
Yes, they're no longer dangling over everything, so it's like a vine, a series of very thick electrical vines. They're out now managed, and we can close the server rack, so we put the doors back on.
It's no longer a fire hazard.
It's been 3 years, but we can now put the doors on the server racks. Quite the accomplishment.
It's beautiful.
I feel like you guys aren't taking this as seriously.
It's gorgeous. I love it. It's awesome.
There we go.
All right. So as we journey further into reverse engineering and binary analysis stuff, I figured we could spend just a quick meeting going over like actual compiling, linking, all that fun stuff, just because I don't know, does anyone here not like is anyone not super comfortable with like binaries and how things are compiled and linked? All right, cool. I figured we could all just kind of go over this. And that way, when we start opening things in Ghidra and IDA, it doesn't throw people for a complete loop.
Just for now, I realize our slides don't have any bytecode on them.
I was just going to open up a command line and start doing things.
Should I compile with Python?
No. All right, so compilation process is pretty simple, but also not. So these 4 little blocks summarize it well. You start with your source code, like C++, or C. We're only going to talk about those 2 today, because that's all I care about. But basically, you shove that into a compiler, which will turn that into assembly, and then that will go through an assembler, turn that into object code, and then that will all magically go through a linker and then produce this beautiful binary. Many of you have probably not seen those like inner 2. If you use GCC, you probably just do like GCC main.c and like you go from source code to executable and you see nothing in the middle. So figured today we could like touch on those 2 in the middle a little bit. So basically compilers, like I said, they translate high-level language like C, C++ into low-level language, or a low-level language. So GCC can actually go to assembly, object code, or machine code. So we'll go over that a little bit. I have a little example. So I've only ever used GCC. I've never used Clang, but I thought I'd throw that on there just as another compiler. But GCC is actually a collection of compilers. I can do C, C++, Java apparently, and Android and iOS, which I have also never used. I've only ever done C, C++. And then a little example. GCC is big. We'll open up the main page. It's big. But Clang is also another compiler. It tries to aim for fast compile times and really useful error/warning messages. That's the extent of my knowledge of Clang because I've never used it. I think Zach said that GCC is an alias for Clang on Mac.
Yep.
Fun. But yeah, so that's what a compiler is. So assembly code, if we go back here, what's that next step? So it's basically just a low-level language. It corresponds very closely to the actual CPU's architecture. So like x86, x84, x86, MIPS, ARM, like all those different architectures. The assembly will actually correspond to the actual instructions to like manipulate the registers and memory. So there's really 2 different kinds of assembly. RISC is like very structured, and then or like the label is very structured on like what qualifies as a RISC, and then CISC is kind of the catch-all for everything else. So RISC stands for Reduced Instruction Set Computer. It basically has a smaller set of simple instructions that aim to do like one thing per CPU cycle. So on the right here you see like load. This is a really good example I found online that like shows the difference between RISC and CISC. But you see on the right there it says like load whatever's at 2, 3 into A. So like the load command does one thing. So there's definitely a separation between like arithmetic operations and memory access. So on the other side, CISC, each instruction can perform arithmetic and memory operations. So a good example of this is multiply, which you can see on the right there. So in something like x86 or x64, you can just be like, hey, multiply these two numbers, and under the hood, it'll say, hey, do all of these, like RISC would. So load this memory address, or what's at this memory address, into this register, get the product of that, and then like throw it back up in memory. So that's really all we're going to talk about assembly today, because that's a whole nother meeting in itself. But yeah, those are the two types of assembly. Oh, also instructions are not uniform in length for CISC. RISC, they're usually uniform in size. I know MIPS is like 2 or 4 bytes. Can't remember. But if we look at some assembly later, you'll see that like different instructions are different sizes. All right, object code. Go back. Here we go. Got our object file. So after your stuff goes through an assembler, it becomes really readable after that, because you get an actual binary. But the stuff that's in object files, it's really just an intermediate format. It's not directly executable itself. So if you were to open one up, or if you were to run file on it, you would see like, oh, this object file. Okay, cool. So, y'all read that? Yeah. So we'll look at this make file real quick. This make file basically just takes this main.c, which I'm pretty sure in its current state just says like a is equal to 5 or something really, really easy, so the assembly doesn't get out of hand. But you can use GCC and throw it the -s, and it will actually drop the assembly. So it'll kind of just stop, and it won't go forward and generate object code and or an executable. And then -c drops an object file, and then just like the normal GCC. -o is output, so you can say like what the name is. Usually it's a.out. So for object files, if we run like file, nope. You can see that object files are still ELFs, though they're not executable directly. So we try to run like obviously that won't run because it doesn't have an entry point or anything like that. So we do object dump. I think it's X or D. Object dump is a really interesting tool for looking at binaries. If we do -x on this object file, you can see that it kind of looks like an executable a little bit. If you've ever looked at executables before, we've got like our .text, .data, BSS. We'll talk about what each one of these is in a little bit, but if we do, actually let's look at the main. No. All right, yeah, it's a really simple binary. It just sets a equal to 5, so really clean. All right. So if we run object dump -d on main.o, so you can see that the object file actually has like a compiled version of our source, but you can see that in the text section there's like just this main, so you can't execute it because there's no libc underneath it and there's no entry point or anything like that. So that's that, but we'll play around with that a little bit more in a second. So we said it was an elf. So I thought this was really interesting. The elf format can be used as linker input and output. So you can basically shove a bunch of object files into the linker and it can spit out like a shared object or a library that are both elf. So elf is pretty cool. It's really complex, but also really cool. It's basically just a structure to a binary. I thought this was a really interesting image. You guys probably can't read any of that, can you? No? All right. Maybe we'll just skip it. If you want to look at these slides, this...
The other one, turn the other one on. Or on.
The other one on off?
Yeah, then it'll take over that. Oh, I guess not.
No, it's the ones back there.
I thought it was the ones there.
Someone want to grab the lights, please? There we go. Is that slightly more readable?
Yeah.
All right, sweet. So this kind of goes through the compiling and linking phase. The link to this article is actually also in the slides as well. So if you want to take a look at that, I thought it was a really interesting read. So we can see here we've got this main.c file, and we've also got this library.h, which basically exports these function declarations of like function one. We've got also this library.c. So when we send this through the compiler, drops out these object files, which inside basically you've got these function definitions that came from this library.c. So it's just like the actual compiled binary version of those. And then you've got this main.o, which is like, hey, call these functions. So they'll compile separately and they'll be fine, but if you try to run them, obviously they won't run. But they don't really know anything about each other than like this one knows that there's these functions that it needs, and then this one has them. So that's kind of the job of the linker, is to take these two object files, and then this one says like, hey, I have these functions that are undefined and I need to use them. And then this one is like, hey, I have these functions that are available for people to use. So it'll take those and package them up together and then drop them into an actual binary. But that's really the extent of it. There's a lot more that goes on under the hood, but surface level, that's what's going on. We'll talk a little bit about libraries, just because you might see them from here on out. Specifically with Linux, shared objects are basically libraries that you can use for dynamic linking. So you can say, hey, I have this library and I want to use some of the functions that are inside of it, but I don't necessarily want to package them up in my binary. So I'm going to use them at a later date. So you can, like we see here, it's present at compile time, so the compiler can actually see like, okay, I know these functions are present, I know that they're real. We can compile against them and create this executable, but we're not necessarily going to include the code from them. When we go to actually run it, our linker will be responsible for going out and grabbing those and using them. Shared objects or shared libraries allow for smaller binaries, so if you're not packaging up that code, obviously your files are going to be a little bit smaller. It also keeps you from like recompiling things over and over again. So if you have an update to, your shared library, you just recompile the library, and then your other binary can just reach back in and use it whenever. You don't have to recompile this binary over here. So kind of the opposite for static libraries. So that -a is archive. And then, like I hinted at earlier, you can use object files to kind of emulate libraries because you can package up object files with each other. That's where things get really weird. But yeah, so static libraries, they need to be present at compile time because they actually get baked into the final binary, which in the end makes it larger. Benefit, no dependencies, so you're packaging up all that code and you're shipping it out, so wherever you run it, it's not going to need to go out and find other libraries. Chris added this, that they're both still executable, which I thought was pretty interesting.
They don't have to be. If you include a main, it will be executable though.
Yes. So libc is actually executable. No. Libc. So you can see that there's this shared object if we run file on it. Oh, that's a symbolic link. Oops. There, yeah. Oh yeah, PIE for position independent executable. I can remember what the E's for.
I think it's execution or executable. It used to be PIC for.
I was going to say position independent code, but
everyone renamed it for some reason.
I think that the two are separate.
Are they?
Really?
From what I understand, position independent code, the position in the binary gets randomized every time. But
I thought that was ASLR.
ASLR is a min.
They're kind of all tied together.
Yeah.
Really differences. Tell me Stack Overflow. From it. Can only be linked. Okay.
Interesting. All right. Well, that's the thing. Yeah. Position independent code is basically when you compile these binaries, you will generate addresses for things. No, don't move that. All right, yeah, here, this one talks about it a little bit. So if you can see, in here we have these functions. This one's at offset 540, but basically somewhere in your binary, you'll have these functions declared, and that's all fine and dandy when you go to actually compile it, because it's like, okay, I have these functions, but when you go to link it, there's no guarantee that that function will be mapped to the same exact spot in memory. So that's where your linker will have to actually like relocate that and be like, hey, I'm gonna go through and just like shift this over. But that's where pick kind of comes into play, because you can be like, oh, everything is relative to this one base address. So with my experience, it's usually just like the base of the function. Correct me if I'm wrong. But you can just use offsets and not use absolute addresses, and that kind of just keeps things a little bit safer. But yeah, that's that. Linking, specifically with libraries. So static linking, like we've kind of already talked about, it's just baking libraries into your executable, so they're not actually linked at runtime, they're linked at compile time. The text section gets really big. We can actually link libc statically with one of our binaries, and we'll see that it gets really, really big. But yeah, dynamic linking, like I said, you can use shared objects for this, where things are just loaded at runtime. So binaries are smaller, things come in at runtime, but not compile time. So that's really all that is. Executable formats. We can dive as deep into this as you guys want, but kind of the basics of it. Linux uses ELF, Windows uses PE, or portable executable, and I've never used Max, but they're rumored to use Macho or Mako. What do you call it, Zach?
Called Mako, but
Mako. Gotcha. But we'll stick with ELF for now. So ELF stands for Executable and Linkable Format. Like we saw, object files are also ELFs as well as executables. So I don't think there's anything really after that, just calling conventions. Not slide. That's quick. All right. So if we run file on our main, we can see it's an ELF 64-bit executable. But if we do objdump-x on main, that's big. Excuse me. And here's some of its sections. But primarily the ones you'll ever mess with are text, data, and BSS. So text is your actual executable code. That's where your instructions live, where it's like, hey, move these into these registers and do all this cool math. Your data is just data, so declared data. And then BSS is uninitialized global data. So that's really what those sections are. PLT is an interesting one. Can't remember what it stands for. I think it's position and linking table. But that you can kind of say this function exists. Here's how you link it. But yeah, I'm not gonna go over every single section just because we'll probably do this in IDA or Ghidra some other time, and it'll be a lot more fun than this dry presentation. But yeah, we'll briefly talk about calling conventions. We'll again probably go over this when we do IDA stuff, and it'll make a little bit more sense. But basically, when you have assembly and you go to call functions, you have to do it in a very specific format, which is, in this case, it's a C calling convention, where does everyone know what a stack is? Everyone good? Stack? Okay, think of a stack of like books. So like you throw something on the stack and then throw something else, so it is first in, last out. So common terms are push and pop. So you can push onto the stack and like add one thing and then pop, take one off. So when you want to call a function in assembly, you basically push the parameters of that function in reverse order, and then you push your return address, your base address, and then you can actually start declaring variables for that function. So if you have like local variables, you throw those onto the stack, and then I can't remember EDI and ESI what those are for.
Those are the first and second arguments. The register, the pointer to the argument goes in those two registers.
Gotcha. So basically that's how you call functions in C. So you just throw things on the stack and then it makes this nice little structure. I know that was super quick and like super high overview, but I was trying to keep this very dry presentation quick. Does anyone have any questions? No? Cool. That was quick. All right. Next week we're going to do some binary exploitation and maybe a little RE. We have this website called crackme.eu, Crackme.org.
Crackme's that one?
Crackme.1.
What?
There we go.
Previously crackme's.de.
What?
Previously crackme's.de. That's what you're doing.
There you go. So yeah, this is a really cool website. We'll play around with it next week. But basically you can download binaries and then figure out how to exploit them, and they'll just kind of spit out flags. If you want to get ready for next week, come with Ghidra and IDA. I want to start out with IDA just because it's not as easy.
Start with R2.
No. I don't know. I kind of started on Ghidra, and I feel like it's too easy because it just looks like C code and doesn't teach me anything. I want to know assembly. But thank you all for coming. If no one has any questions, we're done here. Cool. We get mac and cheese.